So then Andrews goes on to say that this paper is mainly concerned with the rates of marginal recession of the Laurentide ice sheet, with particular emphasis on the retreat rates experienced during the deglaciation of the northern United States and southern Canada and the Canadian Arctic between 18,000 and 7,000 years ago. Of primary concern is the energy balance at the margin of the ice sheet required to promote the rapid late Wisconsin retreat. And he goes on to say that the growth and the development of the Laurentide ice sheet complex is still an enigma. Now, he was saying that in 1973 after about 120 years of, in-depth glacial study, right? What was true in 1973 is also true in 2020. The growth and development of these great ice sheets is still an enigma, right? I want to drive that point home. He goes on. He says, unexplained is the growth of the ice cap in its gathering grounds of Baffin Island, Labrador, and Keewatin, where at least today there are low winter accumulation rates or accumulation regimes. Equally unexplained is the southward penetration of the ice sheet to latitude 40 degrees north or so, where even under full glacial climatic conditions, mass loss at the southern margin might have been considerable. Right? Think about it. I mean, because there's a normal, you think about, the seasonal changes in the northern latitudes where you get heavy snowfall, like where I grew up. You got a lot of snow. I can remember that well because, we lived out there in rural Minnesota on the edge of the prairie, and we had a burn pit, a burn barrel that was maybe 150 feet from our house. And one of my chores was to take out and burn the trash. So I would do that regularly, maybe once a week or twice a week or whatever. So late fall would come, the snow would start, and I would shovel a pathway. By the end of March, before the spring melting started, I was in a slot canyon that was about 6 or 7 feet deep, right? Yeah. Now, end of March, 4 weeks, 5 weeks later, boom, that's all gone. It's melted away, right? So in an ice age, that doesn't happen. I mean, I could go up to Canada now. We were just looking at a map of Canada up in Quebec. Same thing. Every year, you're going to have many feet. You're going to have feet of snowfall accumulating. Come spring, it's all gone. Now, when you have the onset of an ice age, basically, you're looking, right? Not there. Anyways, you have really what would appear to be an instantaneous change of climate. Because think of this. Imagine now that you have normal winter in northern, over North America, northern United States, Canada. You have a snowfall, but then come spring, that snowfall doesn't melt. Come end of summer, that snow is still there. So basically what you're talking about is that you go from a climate, an interglacial climate, to a climate where, boom, it's like you get winter, but then the winter lasts for 10,000 years. You see? So now you've got this glacier growing to the south, and you've got the normal seasonal melt back that you would expect. Well, see, that further compounds the problem. And that's what he's talking about there when he says that even under full glacial conditions, mass loss at the southern margin must have been considerable. So during the growth of an ice sheet, which apparently grew really fast, I mean, in a geological sense, I mean, at 25 or 26,000 years ago, the ice mass was very diminutive compared to what it was 5,000 years later, 6,000. By 18 to 20,000 years ago, you had late glacial maximum. Now, in the literature, I've seen dates with a spread of maybe 3,000 to 4,000 years as to when the actual LGM or late glacial maximum was. Some of them put it at 18,000 and say, the melting was already underway by then. Other studies suggest there was no really melting until somewhere between 14 and 15,000 years ago. So who's right? We don't know, but I'm sure that in the next few years, we're going to get more data on that will allow. I'm at this point tending towards the younger dates, that maybe the full glacial mass was still intact at 15,000 years or later. But in any case, the problem with the rapid growth of the glaciers is that they grew so fast that it's hard to explain, well, how could they have grown that fast? Because the growth rate, you see, was as fast as the recession rate. So if it's growing, say, at 260 meters a year, but then the summer comes and it's supposed to be, receding, melting back, well, then you have to somehow have a net increase of X amount. So that means that really during the season when it's growing like twice as fast. You see what I'm saying?
Yes.
Yeah. So that's the problem that he was asked. So the commenter was asking about the energy problem of the melting. And I think that's sort of what you're getting into here, is that there's an energy problem with the accumulation as well. Yes.
Yeah.
Equally unexplained is the southward penetration of the ice sheet to latitude 40 degrees north or so, where even under full glacial climatic conditions, mass loss at the southern margin must have been considerable.
Yeah.
At its maximum extent, the Laurentide ice sheet complex was approximately the same size as the present Antarctic ice sheet, which they're putting at 12,653,000 square kilometers. In the last few years, the increasing number of radiocarbon-controlled marginal positions, led by Bryson et al. In 1969 and Prest in 1969, to produce isochrone maps on the deglaciation of the Laurentide ice sheet. These maps have been used to estimate the changes in area and volume of the ice sheet as a function of time. The average annual rate of marginal retreat of the Laurentide ice sheet, calculated from the reduction in area, was 260 meters per year, or 853 feet. This high figure immediately raises the question of what energy sources are available to cause such a rapid retreat. A significant aspect of the Laurentide deglacial history is the high energy inputs required. The paleoclimatological conditions at the southern margin of the Laurentide ice sheet during the late Wisconsin have been discussed by many. A significant aspect of the Laurentide deglacial history is the high energy inputs required to produce the apparent rates of marginal retreat. So then he's concluding up, and then this is a figure. I'll pull this figure up in a second here. He says the problem imposed by the estimated rapid rates of retreat is illustrated by figure 7. If the retreating ice sheet maintained a dynamic flow, the profiles of figure 7 represent an approximation of the marginal form of the ice sheet. A retreat rate of 200 meters per year thus requires a tremendous vertical mass loss in the vicinity of the ice margin of at least 10 meters, possibly as much as 50 meters or of water. These are minimum estimates of vertical lowering near the margin, as no account is made in them of the forward movement of the ice sheet itself, which in southern latitudes had to have been at least 10 meters per year. And I will do a share screen here now. We can look at figure 7. All right, there it is, figure 7. So what we're looking here left, the y-axis, notice is in meters. So ground level 0 here up to 70 meters. So it's looking like about 90 meters when you get to the top. And then the x-axis is your recessional rate. And so you can see that if it's receding 200 meters per year, it's moved from the furthermost extent here on the left end of the x-axis. It's moved back, let's say, 200 meters. So what he's saying then is you can see the tremendous volume of ice that has to disappear, right? Now, and then he's pointing out that at the same time, the ice is still advancing. It's still dynamic, see? So
it's
imagine
thicker.
Yes, right. So you've got growing, but it's still receding back at this average rate of 2. And then he goes 300 meters per year. See? So this is this vertical loss, this vertical mass loss. Now, what I would then say, and when I first encountered this decades ago and puzzled over it and thought about it, I thought, well, the assumption here is that you've got a uniform application of energy extending over whatever, 8, 9, 10,000 years, right? But what that is it's the net energy. And it's just an assumption that that would be distributed uniformly through the entire phase of glacial retreat, right? What occurred to me is, well, I think what we need to be looking at is the fact that within that window of time, there were periods of massively accelerated recession or melting, so that the average over this full span of time works out to 853 feet per year. But that's not to say that any given year it was 853 feet. And what we need to be looking at, I think, is that there were, and what we now know from the Younger Dryas, is that here's a period of time where it's even likely that the glaciers stopped receding and began to grow again. Now, if that's the case, look what that does to our window of time and what we have to, the scenario that we have to envision during that window of time. If there's actually 1,300 years where the glaciers are completely stopping their recession or growing again, you see. So now let's go back to the 853 feet on average per year, right? Well, now if you pull out 1,300 years where there's no recession at all, we have to subtract that 1,300 years from the total, right? So now what happens to the annual recessional rate? It has to increase even further.
Yes.
So as we get into this, I think you're beginning to see the problem. And this is why, problems of rates of retreat.
Right. And it's looking at that graph, it shows you perfectly how much larger rates of retreat is a big problem, because there's this enormous volume of ice involved in that. That we're talking about a linear distance, but it's actually a 3-dimensional volume.
An increase in volume as well.
Exactly.
As you recede back.
Right. Because you look at that little 10 meters per year decrease, and it's just a thin line.
Right. Right.
The more it recedes, the more that volume increases because of the shape of the entire
and see
object.
What this 10 meters per year represents is sort of the old extended uniform version compared to what they were now realizing in the 70s.
Right.
So that kind of puts it in perspective.
It does. That's really cool.
Yeah. I think that we'll go one more slide. One more quote here, I think we'll finish up JT Andrews here. We got to,
okay. Sure.
Let's do that.
Jumping the gun. Because
he gets into some stuff here that addresses directly, I think, was it David's question? Daniel. Okay. So with the extended, the higher marginal recession rate, that means 45 meters of water, right, translates into a depth of 45 meters of water, which is going to be almost 150 feet of meltwater now produced, right? He says if a mass loss of 45 meters of water is converted into the energy required to melt so much ice, then a minimum value would be 360 kilocalories per square centimeter per year at the southern and northwestern margin. It is necessary to look at these estimates in the light of available energy sources. Net radiation, referring to solar radiation, is the primary energy source over most ice surfaces that leads to ice melt. Although with an increase in maritime influences, convection and condensation increase in importance. Net radiation is a complex heat source. It is the net product of incoming global and long-wave radiation and outgoing long-wave radiation, and consequently is not an easy parameter to model. In the area of the former southern margins of the ice sheet of 12,000 years before present, the present annual net radiation amounts to 40 kilocal per square centimeter per year. Now, that just means 1,000 calories per centimeter per year, right? 40. Now, what he's saying is that if you're melting back 45 meters of water per year, that requires 360 kilocals. So think of this. Now, this puts it into perspective. If the present net radiation is the primary energy source over most of the ice surfaces that leads to ice melt, right? So here, what's happening now is that he says that in the area of the former southern margins, the present annual net radiation is 40 kilocals per square centimeter per year. Okay, with present radiation, there's no accumulation of glacial ice, is there? None whatsoever, right? So if you go up to the northern United States, if you're in New England, if you're around the Great Lakes, et cetera, net radiation, 40 kilocals per square centimeter per year. Well, basically, to get that 260 or 853 foot marginal recession, you need 9 times as much energy.
Wow.
So just let that sink in. Digest that for a minute. How the hell do you explain that?
Right.
Now, this would be 9 times as much energy extended over 8,000 or 9,000 years. That's the total amount of energy to get rid of that effing ice mass.
Wow.
Right? So now you can begin to see problems of rates of retreat.
Yeah.
Yeah.
And so then, what was it, 40? It's 40 right
40
now?
40 kilocals.
40 kilocals right now.
Per square centimeter per year.
Right. So I'll take it back to during the accumulation phase, and when the glaciers were growing, it must have been much lower than that up there.
But here's another problem.
All that water had to come from somewhere.
Right, which requires heat transport.
Right. So that's wild. It must have had a point where, like you said, it's constant winter for 10,000 years, and yet somewhere we've got enough heat to make all this snow.
To accumulate 6 million cubic miles of ice.
Right.
But bear this in mind, Russ, the debate on climate change is over and the science is settled.